Thanks so much for being with us, Bob. It's a pleasure. Let's do some Plastics 101 first. I think a lot of people might be surprised, and probably not pleasantly, to hear exactly how much of what they throw in their blue bin actually gets recycled right now. Give us the numbers.
Yeah, I think this is something that I think is a real disappointment when people see these numbers. The reality is that, when you get different sources, and it of course is ever evolving, but, anywhere on the order of, 10 to 15% of that material actually ends up back and recycled. So, in terms of the rest of it, it's either sent to landfill, it's sent for energy recovery where it's used as a fuel, or it's left in a durable product that stays in use, right? But the reality is it's a very low level, right? And compared to other industries, there's significant gaps there.
And I do know the percentages in the U.S. are actually lower than in many other industrialized countries. You go to a place like Japan or many of the European countries, much higher recycling success there. Why is that?
Well, I think in Japan and Europe, I think is another good example where there's a much higher recycling rate. Like in Europe, where you may see over 30% recycling of plastic materials. It's because of regulation. It's because of the infrastructure. It's because of consumer acceptance of the process. I mean, now these are complicated trends, but it can't simply be solved by setting a target, right? It requires that, one, you engage consumers. Two, you provide a mechanism for doing it. You have to have the right collection. You have to have the infrastructure to handle that waste, to sort it, to put it into the right pockets at the end for use. So it's a consumer piece, it's an infrastructure piece, it's an overall process, and of course driven by some regulation value that makes that system work, right? And that's a critical piece of the equation.
So it's important for people to understand that with plastics, it's complicated. These are long polymer chains, and simply throwing a plastic bottle into a bin and melting it and letting it, congeal into a pellet and reusing it, that doesn't generally work, does it?
Right. I mean, it is more complicated than that. I mean, the reality is, what are some of the complications, right? I mean, number one, plastic comes in all kinds of formats, right? I mean, aluminum cans, if you take that as an example, I mean, they come in a common format and easy to separate. But plastic come in many different forms. They come in durable, rigid forms. They come in flexible films. They come in large articles, small articles. So number one, you have a complexity of the format. Number two, they in many cases are produced in mixed material form, where many plastics might be combined together to make an article. And those mixed materials then also have different properties. And so when you try to process those, that adds complexity. Then you add additives, colorants, other materials, maybe even paper, metal, and other materials that are mixed with the plastic can also add complexity to that mix. So that, in and of themselves, the products that they're used in are what's complex, and that's what creates a lot of the challenge.
Why don't you give us a few specifics about what you're doing? This facility in the Netherlands, which you're standing up right now, which has the ability to chemically recycle, which is fundamentally different than mechanical, and might be worth a couple of words on the difference there.
This really started with our foray into this TrueCircle platform in 2019, where we launched the first products using chemical recycling. The goal of mechanical recycling is to basically not modify or alter the material through the processing. Take the waste plastic, reprocess it through melting it and reforming it. Chemical recycling is really taking it back to its building blocks, really. It's really taking it back to a starting material that can then be used to produce fresh material at the end, or virgin material as we would call it. So there's a big difference. We took that original foray of taking the risk of bringing that feedstock into our assets, producing the first materials. The reality is that the engagement with brand owners and with our customers was tremendous, to the point where we easily overcommitted that volume and realized that we needed to move forward with how do we actually scale this. We've now, as you highlighted, just announced the construction is starting for our next scale-up, which is in the Netherlands at our Helene facility. And that will produce a larger amount of that material that can then be processed through our footprint, our crackers as we call them, to produce olefins and then produce polyethylene, polypropylene, and other materials. And the goal is to take that to another scale such that by 2025 we're producing 200 kilotons per year of the product.
Your customers, consumers, they're prepared to do this. They're prepared potentially to pay a little bit more even.
Correct. And that's already happened. It happened in the initial launch. It's certainly happening at the scale that we're at now. And obviously it will happen as we go forward to the larger scale. So I think that's where our focus is delivering it with the best technology we have today, but ensuring that there's a pipeline of solutions that can bring the costs down for the future.
Did that surprise you a little bit that there was that kind of demand?
Yeah, I think it doesn't surprise me today, but I think if you would ask me that question 5 years ago, I think we would have gotten a different answer. And go back 5 years ago, the goal was efficiency, cost, performance, solutions that could enable more complex packages with better attributes, like things like how sealable the package is, or how tearable it is, or maybe can I reclose the package, or what coloring or printing can I use, and also caring about the efficiency, right, the waste in production and those sorts of issues. But clearly today that's a piece of the equation, but it's clearly balanced, right? It's balanced with, can I recycle this package? How complex is it to manufacture? How complex is it to handle? All of those other issues. And so I think you're now getting a much more holistic view of the consumer and value chain need, and that's what drives investment.
It's interesting. This makes me think of Thomas Edison, believe it or not. His first invention was a device for legislators to use to count votes, and he patented it. But the lawmakers, the politicians, didn't like it because it made it impossible for them to do the politicking and lobbying that they wanted to do. So it was a great idea, but nobody wanted it. What you're talking about is a great idea. It's important that people want it.
That's right. I mean, I think that's, at the end of the day, the consumer voice and the consumer buying power has a huge impact on the value chain. And so I think the company is willing to take some risk to pilot solutions that are not 100%, fully worked through, but are in the direction of goodness towards where we're headed, and engaging with the value chain to learn, so that when they do their next scale, they're taking the right investments to make that, an even better solution. I think that's what this journey is all about for the next decade. And look, I do feel like the industry is clearly not only on board, but taking an active leadership voice and making that happen. But back to where you started, it also requires continued engagement from the consumer in making that value and that need apparent, right, to the brands, to the rest of the value chain, because that's what's going to drive this.
Yeah, that iterative approach, that's very Edison-like as well, right? He said he never failed. He just made 1,000 mistakes before getting the right answer, right? That's kind of what you're doing.
Yeah, I think that's the fear. I think for the industry is that, typically we make very few changes in some of our big unit operations because the capital, as I highlighted, is significant. These assets last for decades. So, you spend years developing research, refining a solution, testing it, ensuring that it's improved enough over the previous versions that it makes that investment worthwhile. And then you bring a perfect solution to the market for that time, right? I mean, that's traditionally how the industry worked, so that you can ensure that return on that asset investment. We're in a reality right now where we have to be more iterative. We have to take some risk. We have to test these concepts out in a smart way. And we have to use the learnings to design what that end state is going to be. And I think it will be an iteration. I for sure believe that that's the case. But I know that not acting now and waiting for this sort of perfect solution is not going to be the path towards solving it.
Are your competitors thinking the same way?
Yeah, I think each company in our petrochemical landscape is engaged in this space. They all have differing approaches, differing balances of whether they're focusing more on mechanical recycling or advanced recycling. And again, I think some of that comes down to what is their strength, where do their products fit, what expertise do they have internally. So I think all are looking at that, all are engaging in different ways in it. I'm not going to say that one company's solution is going to be the right one or the wrong one, but we're all engaged in that, right? And I think in general, we're also collaborating in many cases bilaterally, trilaterally, and more with each other, right? Because I think we're recognizing that one way to mitigate that risk in these early stages is to take some of that capital risk together, right, to test these solutions out. So I think you're going to see more and more of that. I think what I'm proud of for SABIC, and I'll maybe focus on SABIC, is that we recognize that all of those pillars that I highlighted are important, that we've got to work on the business model. We've got to work on how to design things differently, like in design for recycling. We've got to work on mechanical and chemical or advanced recycling. We need to work on all of those, and that holistic view of the problem and recognizing that we're going to learn as we go as a company and take some risk, I think people don't recognize, to take the step to put this feedstock into our running assets the first time to produce this, that's a significant risk for the company because all your downstream assets are connected to this risk. But that's the kind of steps we have to take. Smart, controlled, thoughtful risk, but with an objective in mind, which is to learn and to rethink how you design things for the future. So I'm proud of what we're doing. Again, I think the industry as a whole is really engaged in driving this. But I think it's as a scientist, which is, taking a step back, it's also a fun time because I think there's a huge amount of innovation opportunity. When you have a disruption and a need like this, that's when, real innovation happens because you're meeting an in need of the consumer at the end that's driving the priorities of that investment. So it's an exciting time to see that happen and to see some of these things come to scale.
I want to go back to that plant in the Netherlands for a moment. If everything works as you hope it will, how much bigger a piece of the pie will you be able to address with plastics recycling? You mentioned those small percentages up front and the complications of how complicated plastic is and the layers and all that sort of stuff. How can you get a much bigger bite out of the problem at this one plant?
Yeah, in terms of the mix of materials that you can process through a facility like that, it allows you to tackle a much bigger piece of the plastic value chain. So there are certain materials that are maybe less suited because of the materials that are incorporated in them that lead to impurities in the stream. But you can address really the large volume of mixed plastic waste, and you don't have to separate all of that mixed plastic waste to process it through these facilities. So that's really the advantage of advanced recycling or chemical recycling. Is that, although there are some materials that may lead to impurities that have to be addressed, you can address the larger volume of mixed streams without having to do the same degree of separation. Whereas, again, mechanical recycling really requires you to take polyethylene, polypropylene, polycarbonate, and do your best to sort of consolidate and separate those streams. So that's what's exciting, is that I think it has the potential, especially where you can aggregate the waste effectively in large areas, that you can build scale on the conversion. You can address some of the complexity and cost on the waste sortation and collection side because you don't have to separate it to the same degree. And you have enough volume that way that you can drive scale of these solutions, right? And scale at the end will drive costs down. And so the plant in the Netherlands, it will still be a small scale in the grand scheme of the equation, but demonstrating at that scale will tell us that it works at a global scale. And that I think will also show us what it takes cost-wise for the long term to get that scalable for the industry. So we're going to learn a ton in that to help us in that next phase. And again, I think will help the industry as we learn and as others do similar pilots in the coming years. I think that picture of where we can go with this will be clearer. But to where you started, absolutely the benefit of advanced recycling is that it allows you to address the broader mixed plastic waste streams.
I don't want to overstate it. Can you throw just about any kind of plastic in one end and out comes virgin material on the other?
That's essentially the idea. I mean, there are obviously exceptions. There are some materials that contain higher amounts of chloride and other materials that will have to be addressed. But some of those may be able to be addressed by downstream purification and cleanup. So again, I think the focus will be, how do I broaden the amount of plastic that comes in the front? And how do I also work on purification mechanisms that will allow me to continue to broaden that? So we're working on both of those, right? How do we do the conversion? And then how do we process that material such that we can manage a much more diverse mix of plastics? Because that's the goal. The goal is to simplify it as much as possible on the front end.
So to do something like this, though, you need catalysts and you need a lot of energy. At the bottom of the ledger, does it all work out, especially if you're using fossil fuels, for example, to generate that electricity?
Great point as well. So, look, if you look at sort of life cycle analysis, for example, right, and you say, look, the current slate of these materials, one of the common outlets for these materials today is when they're end of life, they're incinerated. Japan used that example as a clear one. Europe is another example. To do chemical recycling or advanced recycling definitely requires you to take that material back, to process it with a lot of heat, so a lot of energy goes in. You have some waste. Some of that, recognize some of the byproducts that are produced in that conversion are used as fuel, so there's some efficiency in the process. But at the end, versus incineration, you save about 2 kilograms of CO2 per kilogram of product by doing chemical recycling versus incinerating it. So it's way better solution in terms of CO2 to do that. But clearly where the direction has to go also is, how do I look at renewable energy sources, electrification of the heat versus using fuel as the heat, so that I can take CO2 out of the equation. So you have to, so as a first step, it's a significant improvement from a CO2 footprint. But from an investment of technology, we have to look at how we convert to renewable energy versus fossil-derived feedstocks for the heat, as you highlighted. And that's a clear area of focus. And that's an area of focus, just as an aside, for the whole industry. We just made an announcement with BASF and Linde recently on working on how we make olefins, which are again fueled today by fossil fuels for the heat, the energy to drive that reaction, and developing electric furnaces that would be driven by renewable energy as a way to take the emissions down to near zero in our olefin production. Applying similar concepts, using renewable energy and electrifying the heat generation and the processing of waste is the next step too. So clearly, these are areas of clear focus for our company as to how do we, one, invest in renewable energy, and then how do we also start electrifying our assets. And where you typically think of, obviously mechanical equipment is one place to do that, but where heat is generated is the biggest CO2 producing space, right? So where you generate heat today to drive an endothermic reaction using natural gas or other feedstocks, that's the opportunity. And I guess it's a solvable problem. I mean, we have heat generation with electricity today. But what it means is just redesigning for scale and temperature of these furnaces or these heating elements to use electricity, going through the necessary validation and risk mitigation to make these conversions happen. So clearly, where you ended that, the next step in chemical recycling is how do you look to take the CO2 footprint down further, to shift the energy source on the heat to renewable energy. And again, as highlighted, we're looking at applying it there, but also throughout our whole asset footprint. Because we see that renewable energy and that transition is key for the industry.
On the one hand, we might think of this as producing more plastic at the other end, but there's any number of ways this could go. And there's a term which I think people should become familiar with, which is upcycling. Why don't you explain what that is and how that fits into the whole cost-benefit analysis of something like this?
Yeah, that's right. I mean, look, I think, when we talk about mechanical recycling, which again is kind of what we normally, think of as recycling. All right, I'm going to take the material, I'm going to reprocess it and melt it down and reform it. It's the simplest, lowest footprint, usually most cost-effective solution. But you almost always downcycle there, right? And what does that mean? You downgrade performance. You take a material that was designed for some use, you then melt it and mix it with other materials that don't have the same performance, and you end up with a new pellet that gets processed that has a mixture of additives, a mixture of materials. It's not as pure. It's been heat processed, so it's got some degradation. And so almost always in mechanical recycling, not always, I mean, there are examples, but in most cases, you're downcycling, you're downgrading performance. You're taking it from a high end of performance to something more tolerable. From a cosmetic container to a carpet material or something like as an example, right? So upcycling is the opposite, right? It's how can I take waste material and move that into higher end applications, and I think that's the advantage of advanced recycling or chemical recycling is once I take that waste and I bring it back to its building blocks, I can make all the materials that I want to make. So I'm not limited anymore with sort of working with the material that I have. Once I bring it back to its essential building blocks, I can now make, take a waste material that maybe was used for a lower end application that had less requirements, and I can now convert that back to building blocks and into a high end application for a food product or medical packaging or personal care or hygiene application. So, you now open up the suite of areas where you can apply this. And of course, that is definitely an upgrade in value at the end as well, to your point, right? And that's also a way to help drive the economics, right? Is to be able to take, say, for example, a lower value end product or mixture of materials and get them into a high value application.
So I hesitate to say this to a PhD chemist from Caltech, but it sounds a little bit like alchemy, right? Hang on to your wallet. It sounds too good to be true, that sort of thing. If it all is so possible right now, what are the stumbling blocks? Is it economic? Is it a lack of regulatory impact? Is it the industry worried about its bottom line, or is it something else?
I think you covered a really good list of the challenges, right? I mean, I think so. I mean, again, it sounds too good to be true because nothing is that simple, right? I mean, the reality is that one, as highlighted, our industry is built on building assets that last for decades, right? So number one, to displace what exists, you've got an existing depreciated infrastructure, right, that you have to address. So, it requires investment in new processes, new technologies, new footprints that would displace the existing ones. So there's an economic barrier there, right, which is capital going into displacement. But at the same time, there's sort of an inertia with that too, because you've got an existing asset base, you have existing products. So there's that piece of the equation, which is an economic one, and more of, as you said, a cultural one, which is it's a disruption for the industry, right? But you also have back to the regulatory side of the equation and the waste infrastructure side. What will drive the economics is an understanding of the value of the materials that are going through that flow. I mean, today, we don't really put a value on that end plastic at the end of its life, right? It's a waste product. The reality is it has inherent value in it. It has inherent fuel value. It has inherent monetary value. And, as we work, through, with the government agencies, with the regulators, I mean, I think this is the key part of the equation, which is, how we manage that waste, the value we put on that waste, how we set up the right investable economics for the waste infrastructure, giving them a value for that product at the end versus landfilling it. And then how that translates into economics for investment in our ecosystem is a key part of that. So there's clearly a regulatory piece, right? Understanding the value of the plastic and potentially the cost of these materials. And by cost, I mean, increased cost for disposing of them, which will be an implication. That cost and value of those materials is what will drive the investments in the infrastructure. And so that's a critical piece. So there's definitely a regulatory piece. There's definitely an economic sort of barrier piece. Lastly, there's just a risk piece, right? I mean, honestly, you're going to make materials that have been weighed a certain way since World War II. I mean, olefin cracking, which is the way, where we take, oil or natural gas and crack that to make olefin, ethylene, propylene in the building mix. That's been around since World War II. This is, it's obviously been optimized and improved to be more efficient, but it's an extremely efficient, low-cost way to make those products. And you're now moving into a path where you're doing that, again, in a similar way, but with new feedstocks, new materials that are less experienced with use of them. So I think we just have to recognize that we have to take the right steps on the risk to make sure that we can run all these materials in our existing assets. We have to make sure that we understand what that material is going to cost us and what the value of it is in the end. We need to make sure that in the value chain that, again, as you touched on earlier, that the consumer is valuing it, that the brands are shifting the products to take into account these solutions, that everyone is working together towards the same purpose. And that's where, what would be the biggest roadblock is if, one player like the petrochemical industry was trying to push this by itself and there was no pull down the value chain, or a brand owner was pushing it but without any engagement on the value chain to bring solutions to achieve it. I feel much better that everybody understands those issues now. Everyone in the value chain understands many of these hurdles that we just talked about. I think the other complexity, just sort of end on the waste side, is that every region is unique on the waste infrastructure side. I think that's the piece that there's also a complexity that is maybe not, to the consumer, maybe not fully understood. I mean, our waste infrastructure in the U.S. is very different in maturity to that of Europe, and that's very different to that of Southeast Asia, for example. And so, when it comes to how do we solve this problem in the emerging geographies where, as much as we might criticize our waste infrastructure, it's at a much more advanced stage here than it is in these other geographies. I think we have to recognize that the speed to implement this in certain regions is going to take more work. It's why the Alliance to End Plastic Waste, where we're a founding member, is very focused on allocating capital for waste infrastructure pilots in Asia. They're doing it globally, but Asia is a clear area of focus for us because addressing into these emerging geographies, again, with scalable economics that make sense, that's going to be a key piece of it. Right? Otherwise, you can solve it in the U.S. and Europe, but you don't address the waste challenge in the emerging world, right? I think that would be a failure as well.
Yeah, I think when people see those pictures of plastic waste in places like Indonesia and Malaysia, and for that matter, they think about the blob the size of Texas in the middle of the ocean, they get overwhelmed. It's not unlike the related problem of climate change. It's so big, it seems impossible to solve. What do you say to those who say it's a pipe dream, that this is a problem we can't tackle?
Oh, I definitely disagree with that, right? I mean, I think, the example of the waste into the oceans and, sort of this 8 million tons that oftentimes gets highlighted about the waste that's going into the oceans. The reality is the bulk of that comes from 10 rivers that are primarily located in Asia or the East, let's say. It's a global issue, but the reality is it's coming from sources that we control. So this idea that it's happening in the ocean, the issue is the waste is occurring in our communities, especially in communities where there's poor waste infrastructure, where there's access to rivers, and that material then funnels from the rivers out into the ocean. So addressing the challenge is definitely feasible. It requires a different way of thinking about waste collection at point in the emerging geography. It requires scalability of the processing solutions. But if you just take the 8 million tons of plastic, for example, that people would highlight that leave the environment to the oceans, I mean, that amount of material, if processed through advanced recycling, would fill up a couple of plants. It's not an insurmountable amount of material to process in the industry's footprint. In fact, it's actually a very small percentage. But you can't solve it without all this work, right? You can't solve it without addressing stopping the flow of it first into the oceans. You can't stop it without then addressing how do I convert it to something of value, because today it's sitting in these geographies having no value. And then how do I ensure that I have the right processing technologies to convert it? So I feel very confident in the ability to address it. I don't think it's easy, right? I think we wouldn't be tackling it if with the power and sort of value chain engagement that we are, if we thought it was this simple. It's a complex problem, but I feel confident that we can address it. Just like, by the way, just to make this point, honestly, I think people felt like paper recycling, aluminum recycling, glass recycling, these were all, big challenges as well. The reality is when you make the decision to invest against it, you put the right frameworks in to support the conversion, it happens. It can be done, for sure. So again, that's why I'm optimistic about it.
Do you think if Edison were alive today, he'd be tackling this problem in some fashion?
Yeah, I think he would probably still be on 3 hours of sleep a night, inventing away with ideas. But look, I think this area and again, the broader climate change and carbon neutrality sort of focus, these are just two areas that are just so ripe for innovation that, clearly folks like Edison, but hopefully folks like SABIC employees and BSF and Dow and others, I think researchers are engaged, university researchers, students coming through our educational system. I mean, I think we need people to recognize the role that science and technology can play in solving these problems, that they're not insurmountable challenges, they are solvable and tackleable problems, but that we need investment in science and technology. We need people to choose these careers, to invest themselves in going down these paths, because we need the best minds on these kind of problems.
Well, I think all of us have had a lesson this past year in the value of science. The fact that, I've got a vaccine in me, I don't know about your situation, in a year's time from it all emerging is extraordinary. Science can save us, can't it?
I absolutely agree with that. I went into this field because I was passionate about what science can do. I have my vaccine tomorrow for the second batch as well, so I'm on my path as well. But no, science is a key piece of delivering this, and I think recognizing that we need to listen to our scientists, we need to challenge them, right, on the solutions so that we also think about the end result of the solutions. But we need to collaborate, scientists, governments, and industry together to deliver these kind of solutions to make sure that the infrastructure, the environment around the innovation, and the support for the technology is embraced.
Fascinating conversation. Bob, thank you for your time and keep up the good work.
Great, thank you.